Okay, so the cheetah was in, the cheetah disappeared. Okay, so next talk is by Dakshita remotely. He's going to talk about how to certifiably delete secrets. Okay, Dakshita, you're on. I don't know if we can hear you. We can't hear you.
Yes, can you hear me now?
Yeah, now we can hear you. Perfect. Yeah.
Okay, so thanks everyone for being here, and I'm sorry I couldn't be there in person. I hope that I'd still be able to hear any questions you have, so please feel free to interrupt and ask questions at any point. This talk is going to be about certifiably deleting secrets. It's based on a bunch of recent works. I'll mostly focus on this work on cryptography with certified deletion, which is joined with James Bartusek. I will also say a little bit about follow-up works where techniques in here were extended and to obtain a variety of other primitives with certified deletion, including obfuscation, methods to outsource computation. This is joint work with James Bartusek, Sanjam Garg, both at UC Berkeley, Vipul Goyal at NTT Research, Giulio Malavolta at Max Planck, Justin Reyes at CMU, and Bhaskar Roberts at UC Berkeley. I will also talk about, time permitting, talk about how to make deletion publicly verifiable. Again, joint work with James Bartusek and with Alex Poremba. And finally, I will just mention some results on weakening the assumptions that we need to do publicly verifiable deletion. This is joint with James Bartusek, Giulio Malavolta, Alex Poremba, and Michael Walter. Okay, so let me just dive right in and try to explain what it means to realize this delete button or enable encryption and a variety of other primitives with certified deletion. For the definition, I'm going to start right away with defining it. And to define encryption with certified deletion, let's take the example of a public key encryption scheme. But again, this is just an example. This style of definition will extend to many advanced cryptographic primitives. I won't necessarily cover all definitions, but it'll be obvious how to extend it. So in an encryption scheme that satisfies certified deletion, the encryption and decryption algorithms are as usual. We will only consider encrypting bits. Again, this extends to strings without any complications. The main difference from standard public key encryption schemes is that the encryption algorithm is also going to output a verification key. And also that the ciphertexts will be quantum. In fact, ciphertext will have a quantum component and a classical component. So I will just denote the quantum component with a ket around it and the classical component as standard. The decryption algorithm is, again, as usual, decrypts the ciphertext to give a plain text. Well, this is a bit, so let's just say bits. And the additional algorithms that we will have will be a delete algorithm that, given a ciphertext, outputs a certificate, or this is supposed to be a proof of having deleted the underlying plain text. And there will be a verification algorithm that helps some verifier check the certificate or the proof of deletion, given the verification key VK that was generated at the time of encryption. Okay, so this is just going to be the syntax. Again, I haven't told you what this all means, so let me do that now. Informally, security with certified deletion means that any adversary that is polynomially bounded and has access to a ciphertext and then decides to delete it, generating a deletion certificate new, satisfies the following guarantee. If the certificate verifies, then its verification implies that the bit B underlying the ciphertext has been information theoretically removed from the adversary's view. Okay, so I've just written that down here, this informal guarantee, which is just saying that verification of the deletion certificate generated by an adversary implies that they have information theoretically removed the bit B from their view, whereas previously, prior to generating this deletion certificate, their view actually information theoretically determined B, because they actually were carrying a ciphertext, a public key ciphertext, encrypting the bit B. So the next question is, how do we make such a certified deletion guarantee formal? And to do that, we define the following experiment. Again, this considers an everlasting flavor of security, which says that an adversary obtains a public key and a ciphertext generated by a challenger, and then decides to possibly delete it. And after deletion, is left over with some state row. And the guarantee that we have is that as long as the certificate verifies, we can output the state row. If the certificate doesn't verify, then we don't output anything, we output bot. And the formal security definition simply states that the trace distance, which is quantum analog of statistical distance, between the experiment where the adversary was holding an encryption of 0 versus the experiment where the adversary was holding an encryption of 1 is negligible in K, which is the security parameter. So all this says is that the state row after deletion has become statistically, information theoretically independent of the bit B that was encrypted at the beginning of the experiment. Hopefully the definition makes sense. I'll pause a second to see if there's any questions.
No questions here.
Awesome. Okay, so having defined this, I want to just talk about some applications and some constructions of schemes with certified deletion. This is from this recent work with James Bartuszek. And therein, and in that work, we obtain commitments satisfying this strong type of certified deletion. We also obtained revocable time block encryption, attribute-based encryption, witness encryption, and fully homomorphic encryption satisfying certified deletion. Here, the guarantee is that it's an encryption scheme that satisfies the standard fully homomorphic properties, but then also allows the server to delete, certifiably delete the underlying secrets X. And finally, in the same work, we introduced something called we introduced a primitive called everlasting security transfer. This is in context of two-party and multi-party computation. So you all must be familiar with constructions and the concept of statistically secure two-party computation, where it's often possible to achieve statistical security against at least one of the players in a two-party protocol. In any classical protocol, who the protocol is going to be statistically secure against is a priori fixed and cannot be changed once the protocol begins, because you've already started to computationally leak information to the other party. But the fact that quantum encodings can be used to certifiably delete information lets us build protocols where at the time of running the protocol, one perhaps had security against unbounded Alice and bounded Bob. But then dynamically in between the protocol, they decide, well, we actually wanted security against unbounded Bob and bounded Alice, and they can, in fact, transfer unbounded security from one player to the other. I won't get into how this is constructed necessarily. So maybe if we have time, I'd be happy to say a little bit about it. But it turns out that these same principles help achieve these types of guarantees also in two-party computation. Now let me mention some prior work in the area. This idea of revoking information was explored by Unruh in the context of time block puzzles. He built something called revocable time block puzzles, which can be thought of as a time block puzzle where an adversary holding a time locked encoding can certifiably delete the underlying encoded message by generating a quantum certificate of deletion. The concept of certified deletion, specifically also with classical certificates, was introduced by Broadbent and Islam, who also introduced this terminology, certified deletion, and they built one-time pads satisfying the certified deletion guarantee. So these are information theoretic encodings. We're all familiar with one-time pads, where the guarantee is that once deletion occurs, even if the one-time pad key is leaked after that point, an adversary cannot recover an encoded secret. There was also some exciting follow-up work to this work of Broadbent and Islam, first by Hiroka Morimi, Nishimaki, and Yamakawa, who built public key and attribute-based encryption schemes, assuming non-committing encryption. The flavor of security that they obtain is a leakage-style security definition, as opposed to the information theoretic style security that I just discussed. And also the non-committing techniques inherent to some of these works are inherently limited and not powerful enough, or appears that they're not powerful enough to obtain primitives like fully homomorphic encryption. So those were some of the drawbacks of some of these works. Hiroka Morimi, Nishimaki, and Yamakawa had another exciting work on building certified everlasting zero knowledge for QMA, which is a zero knowledge protocol where which satisfies statistical soundness at the time of running the proof, but also statistical zero knowledge after deletion. So this is a guarantee where a verifier can optionally delete any computational leakage they obtained about the witness, and then it becomes statistically zero knowledge against the verifier. And we all know that statistical soundness and statistical zero knowledge for NP or QMA is in general, we believe this is impossible to achieve, and yet by introducing this flavor of deletion, it becomes possible. So I won't say a lot more about that. Let me just also mention two works that were concurrent with the work that I'm going to be talking about. The first is by Poremba, who built proofs of deletion for learning with errors, and essentially obtained fully homomorphic encryption with certified deletion under a strong conjecture. I hope to be able to tell you a little bit more about this conjecture and how it's proved in the later part of this talk. And so in one of the works that I'll talk about, we managed to prove this conjecture and obtain FHE with certified deletion from the learning with errors problem. And finally, there was this work of Hiroka Morimi, Nishimaki, and Yamakawa, who built variants of functional encryption with quantum certificates. And in an update to their paper, they obtained a lot, many other interesting results on building functional encryption schemes with revocation for ciphertext and secret keys. Again, I won't be getting into all the details of these works, but I do just want to mention that there's a lot of interest and excitement in the area. Okay, so with that done, let me move on to why does quantum information help us realize this possible delete button, and in what situations can we hope to realize it? So before I begin, let me just spend a few minutes, a couple of minutes on background. Let me just pause for a second again and see if there's any questions. Okay. Sorry. Yeah. All right. So let me start with some basic background. In this talk, we'll mostly be using BB84 or Weissner states. These are the 4 states: ket 0, ket 1, ket plus, and ket minus. 0 and 1 are the computational basis states. Ket plus and ket minus are called the Hadamard basis states. Plus is nothing but a superposition of 0 and 1 with a positive phase in between them, and minus is a superposition, a uniform superposition of 0 and 1 with a negative phase between them. These are also called conjugate encodings for reasons that will become clear in a few seconds. And I just want to first mention that there is a notational, just for notational convenience, we can denote all these states but with ket x sub theta, where theta denotes the basis, so computational or Hadamard, and x denotes the value in that basis. So if theta equals 0, then this is the state ket x, which is ket 0 or ket 1. And if theta equals 1, then this is the state ket 0 plus minus 1 raised to the x ket 1 divided by root 2. So this is essentially the plus state or the minus state. Okay, so let's move on. Now, it turns out that if we perform what is called a computational basis measurement, so think of this as passing a photon that is polarized in some direction through a filter that checks whether the photon is horizontal or vertical. So this type of computational basis measurement, when applied to ket 0, yields outcome 0, and when applied to the state ket 1, yields outcome 1, which essentially means that it helps perfectly discriminate between the states ket 0 and ket 1. And it turns out that if you applied a computational basis measurement to a Hadamard basis state instead, which is the ket plus or ket minus state, then what you get in both cases is a uniformly random bit that is independent of the state that you started out measuring. Okay, so a computational basis measurement of a Hadamard basis state perfectly erases information, post-measurement perfectly erases information about the state that one had started out with. Similarly, a Hadamard basis measurement will perfectly distinguish between two Hadamard basis states, always tell you whether you started with a ket plus or ket minus. Of course, I'm assuming that these are all ideally physically realizable, which may not be true in practice, but for the purposes of theory, we can assume this. And also, if you performed a Hadamard basis measurement on a computational basis state, then you're going to lose information. After measurement, you will lose information about whether the state was a 0 or a 1 to begin with. Okay. So now with all that background out of the way, and before going all the way to building encryption schemes with deletion properties, let's try to build a really simple primitive called a revocable secret sharing scheme. So this is just like, secret sharing, 2 out of 2 secret sharing that we all know and love. The idea is that there's a dealer, Alice, who has a secret B, and she wants to be able to generate 2 shares of it, hand over these shares to Bob and Charlie, such that if Bob and Charlie get together, then they will be able to reconstruct the bit B, but each individual share perfectly hides the bit B from the individual owner's view. So if Bob and Charlie are isolated, then each of them has no clue what the bit B is. Okay, so that's the usual secret sharing guarantee so far. Now you may notice that I put ket around one of these shares, so I want one of them to be quantum. And the reason for that is that I'd like to have another interesting property, or I'd like to have the secret sharing scheme satisfy another interesting property, which is revocation. The revocation property simply says that Alice should be able to ask one of these parties, let's say Bob, who's holding the quantum share, to delete the share. And as a result of deletion, Bob should generate a certificate or a proof for Alice that they deleted their share and some leftover state row. And the guarantee is that once deletion has occurred, as long as this proof verifies, so Alice will check the proof, this will say yes or no. If the proof verifies, then at this point, the joint view of Bob and Charlie, which is the residual view of Bob combined with the share that Charlie holds, jointly have become independent of the bit B. So prior to revocation, share 1 and share 2 jointly determined B, but once revocation occurs, row and share 2 have jointly become independent of B. Now you may wonder that, of course, if Bob and Charlie are sitting in the same room, they should be able to use share 1 and share 2, reconstruct B, and then apply any delete algorithm. And yes, so here it is extremely important that this delete procedure occurs in a setting where Bob and Charlie are isolated. So they can be entangled, but they should not be allowed to communicate with each other. Now, if you take the example of a simple XOR secret sharing scheme, for instance, where all the shares are classical, then there is no way to implement this. But it turns out that with quantum shares, one can, in fact, build such a secret sharing scheme that allows revocation. The way one would build it, again, just simply uses those 4 BB84 states. And the idea is Alice will sample 2 strings x and theta, and then generate ket x sub theta, which is nothing but a bunch of BB84 encodings. So the ith qubit in ket x sub theta is nothing but the ith bit of x in basis corresponding to the ith bit of theta. Okay, so these are just a bunch of, think of them as polarized photons that Alice is sending over to Bob. And in addition, so that's what Bob's share is. And we're going to use this to enable deletion. And Charlie's share will contain an encoding of the actual bit B that Alice is trying to secret share with respect to the parity of X that Alice used in order to generate Bob's encoding. Okay? And Alice will also send to Charlie the basis information, theta. So hopefully the construction is clear. Yeah, feel free to ask questions if any.
Okay, we're good.
Sorry.
Yeah, you can continue, Dakshita. No question.
Okay. All right. So how does the revoke procedure work? Well, to revoke to revoke the sharing of B, Alice will simply ask Bob to measure all the BB84 states he received in the Hadamard basis and send all these outcomes to Alice. Now, Alice, on her side, has kept with herself all the Xi's for I such that theta I is the Hadamard basis. And to verify Bob's certificate, Alice will simply check that for all I such that theta I is indeed the Hadamard basis, the ith bit of X matches the ith bit of the certificate. In other words, at all positions where the photons Bob got are actually polarized in the Hadamard basis, Alice checks that it is indeed true that the photon she sent, or the value she encoded, is the same as the one Bob reports to have measured. The really cool property about these encodings is that given just these encodings, and without being given any additional information about bases or X's, they all appear maximally mixed, which means that it's impossible to tell whether this is polarized in the horizontal or the vertical basis, etc. And the best you can do really is measure it in computational or Hadamard or some other basis of your choice, but you don't really have any information about what the polarization was. And so the reason that that's useful is that what that means is that Bob would have actually had to measure almost all of these photons in the Hadamard basis in order to pass Alice's check. And that amounts to deleting X. So recall that Bob had ket X sub theta, and measuring these photons in the Hadamard basis amounts to deleting X from Bob's view. So in other words, Bob's state post-measurement does not contain information about X anymore, and which amounts to deleting B, because all that Charlie has is B XORed with the parity of X. And if X is random and X is gone, then parity of X is gone, so B is gone from their joint view. Even if they learn theta at a later point, once they collude. So hopefully the revocation algorithm makes sense. This is it. This is the construction for secret sharing with deletion. I'm not going to get into the formal proof of this. So I am just going to talk about how this can be used to enable encryption with certified deletion. In other words, building on the secret sharing scheme, the encrypt algorithm for an encryption with certified deletion scheme is just going to send the state ket X theta together with, so recall this was Bob's share, together with an encryption of Charlie's share. And Charlie's share was classical, so it's easy to encrypt this using any classical encryption scheme. So how do you construct encryption with certified deletion? Well, one way to do it, we prove this secure in our paper, is simply have ket X sub theta as the quantum part of the ciphertext and encrypt theta as well as B prime, where B prime is the bit B that was intended to be encrypted, XORed with the parity of X. This can also be the parity of X, just restricted to positions that are that correspond to computational basis states.
Sorry,
Okay.
is theta the public key? Like,
Sorry, no, theta is the basis.
what's the key? I know it's the basis, but
Good. So this is just a public key for any classical encryption scheme. Does that make sense? So,
so theta and X are the randomness used for the encryption.
Indeed. Yes.
Right.
Yes.
So, but by the way, can't we keep B prime in clear?
Yeah.
It's a great question. We struggled to prove semantic security of the scheme when B prime is in the clear. It reduced to some combinatorial construction, which was not clear, how to prove it. So it's open to prove that this is, I think, yeah, we think it should be secure, even if B prime is released in the clear, but we don't know how to prove it. And it's not the deletion that's the problem, it's just proving standard semantic security. Okay, so for now, because this is what we can prove, we're also going to encrypt B prime. All right, so thanks for those questions. Let me move on.
But do you encrypt X2 or X? Sorry. So
good. So X can only be recovered by measuring these quantum states in basis theta, where theta
okay. X is given. Sorry, you give this X. You give both the okay, good. Mm-hmm.
You never give X in the clear as a string. What you give are quantum states, which are encodings of X and in basis theta. And then you encrypt theta. So to decrypt, simply recover theta, measure in basis theta, you get X, compute the parity of X, use that to recover the B. Mm-hmm. Okay, so thank you. All right, so this is the encrypt algorithm. I just told you what decrypt is, so I won't repeat that. Let's talk about deletion. Note that the adversary holds these quantum encodings, and then a classical encryption of theta along with B prime. Recall B prime is nothing but B XORed with some parity of X. Okay? So now it's possible, turns out, it's possible to delete as before. Simply start with get X theta and perform a Hadamard basis measurement. So in other words, to request the adversary to delete, we ask them to measure the quantum part entirely, all the qubits of the quantum part in the Hadamard basis, obtaining a deletion certificate X prime, a residual state rho, and of course, since this was classical, this can be assumed to be a part of their state always. To verify, again, we will check that are the Hadamard basis positions correct. So for all I, where theta I corresponds to the Hadamard basis, let me just say H, xi equals xi prime. If this is true, then verification accepts, and the challenger accepts that the adversary did indeed perform deletion. If this is false, then we output bot. Okay, so that's how deletion works for this scheme. And yeah, since we've already discussed how to encrypt, decrypt, delete, and verify, I'm just going to skip this slide and move on to discussing why is this scheme now certified deletion secure. So recall the definition was the challenger samples a public key and secret key, and a ciphertext, which is an encryption with certified deletion of a bit B, then sends the public key and ciphertext to the adversary, who performs deletion, generating a certificate and a residual state. If their certificate verifies, then we output the state row, otherwise we output bottom. And the definition is that the trace distance between the two experiments, one where the adversary was obtaining an encryption of 0 and the other where they were obtaining an encryption of 1, is negligible. In other words, the two experiments are information theoretically close.
Is the reason you need to encrypt B prime? Sorry to backtrack, but is it that otherwise you can try to decrypt without knowing theta and recover partial information?
So the reason we needed to encrypt B or B prime here, I mean, it's unclear that actually just given an encryption of theta, whether there's any way to recover X and then recover B, given B prime even in the clear, because we think that actually this should still be hidden computationally. It just turns out to be non-trivial to prove. I'm happy to chat about this afterwards. It's a bit technical. So
thank you.
Thanks.
Actually, some new questions here. Right, so for the deletion, right? So whoever has like X, like measures it in the Hadamard basis and then gives it back to the dealer, and the dealer, how does the dealer know what is X under the Hadamard basis? Is an X like some sort of random register, or am I missing something really basic?
The dealer has kept with them a copy of X and theta. They were the one who
I
sampled.
see. Okay, I see. Okay, that makes sense.
Thanks. And they actually need to keep this in order to verify. This is not great, so we'll talk about how to remove this later.
And you're using parity everywhere, so partial measurement doesn't help? Is that the reason why parity appears in a lot of places?
No, it's no, we don't. It's not.
It's not related to
It's just trying to come up with the simplest scheme. There's no deep
Okay.
technical.
Okay.
Thanks for all those questions. Any others? Okay, so if not, I'll move on. The experiment, like I said, says if the certificate verifies, we output the state row, and security is that the two experiments, the two states, distributions, mixed states of the adversary, one corresponding to where they received an encryption of 0, the other corresponding to where they received an encryption of 1. In cases where they actually did delete and deletion did pass the check, these two experiments are information theoretically close, despite the fact that prior to deletion, these were information theoretically far, and the encryption actually determined the bit B. So how do we prove something like this? This is, on this slide, I've just written out the game applied to our particular construction. So what the adversary receives is a public key and an encryption under the public key of theta along with B prime and ket x theta and so on. And to delete, they simply measure the quantum part of the ciphertext to obtain X prime and return it. So how do we actually prove that this row, their leftover state at the end of this experiment, is independent of the bit B that was being encrypted? This turns out to be fairly non-trivial to prove. And to prove it, we will start off by deferring dependence of the experiment on the bit B. In particular, imagine that the bit B was only sampled towards the end of the experiment. So in the beginning, we just encrypt random bits, B tilde, something else, nothing to do with B. And later on, if B tilde happens to be correct and match our bit B that the experiment depends on, then we output the state row, otherwise we output bottom. Now, it turns out that if B tilde is sampled uniformly at random, then there's exactly a probability half that B tilde will match our bit B that the experiment depends on. And so it suffices to analyze this other experiment where we just deferred sampling of the bit B to later, and to prove that in this new experiment, the trace distance between the corresponding two experiments, one where B is 0, the other where it's 1, is negligible. Okay. The next step, so what this helps us do is think about this as a stepping stone to the next step, where we simply purify the experiment. So now this is a bit of a technical term. So let me explain what this means. Here, what we will do is, instead of sending to the adversary these maximally mixed BB84 states, what we will send to them instead are halves of EPR pairs. So EPR pairs are maximally entangled qubits. Zvika gave a very nice talk about entanglement previously. And I'm just going to write down to remind everyone what EPR pairs are. These are qubits that look like 0, 0 plus 1, 1 by root 2. If you take one of these qubits, the second one, and measure it in the computational basis, and you see a 0, then it turns out that the first qubit has also collapsed to a ket 0. If you measure the second one in the Hadamard basis, you see a plus. It turns out that the first one has also collapsed to ket plus. So they have this really nice property. And these are going to help us just create melted experiments where we can see what it is that's been sent to the adversary. So the only change from before is that instead of sending ket x theta, which is what we were sending before, we now create these halves of EPR pairs and send to the adversary the second half of every EPR pair on a register, let's say B. and keep the first part with ourselves. So A is kept with the challenger. And now, because the experiment didn't depend on B until later anyway, we can just send these random halves of EPR pairs along to the adversary, and later on measure the challenger's halves of these EPR pairs in bases corresponding to theta to obtain X later on. So in other words, in this new experiment, we've deferred sampling of X also to a point that is much later in the protocol, even after, in fact, after the adversary has already claimed to have deleted. Okay, so that's the first change we make. It turns out again that suffices to prove that in this experiment, the statistical distance between the experiment where the bit is 0 versus the bit is 1 is negligible. Now, in the final experiment that we will consider, let me just go back a second and point out that in the experiment 2 that we were just talking about, the adversary actually does have access to theta at the time of generating their deletion certificate. So in this experiment, if the adversary was unbounded at the time of deleting, so if the adversary was unbounded, then they can find theta, and they can use theta to measure these qubits in appropriate basis. So they know which one is supposed to be computational, which one is supposed to be Hadamard. They'll measure only the Hadamard ones in the right basis to find the deletion certificate. And since the bit B is encoded using the computational basis states, they will keep information about B with themselves while producing a totally legitimate looking deletion certificate. So in this experiment, if the adversary was unbounded, then they can, in fact, break deletion security. And it's important that the adversary be bounded and not be able to recover theta at this point. So that means that in the next argument, we should somewhere be using the fact that theta is computationally hidden from the bounded adversary in order to complete our proof. The way we do that is we will switch the encryption of theta to an encryption of 0. Now note that this is a computational switch. Because this is a computational switch, it turns out that arguing that experiment 3, where we've made this computational switch, is close to experiment 2 is not going to work out. This is just false. In experiment 3, the adversary's view is computationally close, but statistically far from their view in experiment 2. So we need a different proof strategy. We need to somehow still be able to make use of this computational property, but eventually derive an information theoretic claim. So let's see how to do that. Zooming in on experiment 3, we'll see that it turns out that measuring AI in basis theta I, we are going to be able to recover our bit B as usual as before. The only main difference is going to be we encrypt zeros, and we can sample theta a little bit later. The key insight in our work, and I think I'm going to run out of time very soon, so I'm going to skip over some details, but I'll still tell you the key insight, which is that we will find an efficiently checkable predicate on the adversary state row, or essentially an efficiently checkable predicate on these registers AI that the challenger has kept with themselves. And this predicate, by virtue of being efficiently checkable, will have to remain the same between, or will have to have the same similar success probability up to negligible distance between experiment 2 and experiment 3. So it'll turn out that the probability that this predicate holds in both these experiments is going to be close, and that will follow as a result of the computational hiding of this encryption scheme. And then we will show that the fact that this predicate holds in experiment 3 implies that it also holds in experiment 2. And the fact that it holds in experiment 2, despite the adversary having an encryption of theta with themselves, will tell us that the bit B is information theoretically independent of the adversary's view, even in experiment number 2. Okay, so just to summarize that, really quickly, we will show that there is some predicate on the halves of EPR pairs AI that the challenger holds with themselves. That is true for experiment 2. to prove that it is true, we will rely on this mental experiment 3 and show that it holds in experiment 3. And because this is an efficient predicate, all efficient properties should be true with the same probability, regardless, even given computationally indistinguishable distributions. So we'll use that fact to prove that there's some predicate on AI that holds in experiment 2, and use that to derive that the bit B is statistically hidden from the adversary. Now, let me just tell you what that predicate is. The predicate simply says that the registers AI are all close to Hadamard basis registers. So what this means is that whenever the adversary generates a deletion certificate that passes verification, then the registers AI are close, for a definition of closeness that I will not get into, to all being Hadamard basis states, all of them. Not just the ones that where theta was supposed to be Hadamard, but they're all Hadamard basis states. And now this is great because what happens, note that what happens is that we get X by measuring AI in basis theta I. So that means some of these Hadamard basis states are going to be measured in the computational basis to get Xi's. And then we will take the parity of these Xi's and use it to mask the bit B. So we're measuring Hadamard basis states in the computational basis. And as I showed you in those quantum background slides, if you measure a Hadamard basis state in the computational basis, you get a uniformly random bit. And so this gives essentially a uniformly random mask that is being used to mask the bit B. So unfortunately, I think that's all that I have time for. So I'm going to skip the rest of this proof and just say a little bit more about the results. Just say a little bit more about results in other, can I take 5 more minutes since I don't know what is the.
Next.
Sorry, I couldn't hear
Maximum
you.
size that you okay?
Okay, yes. So, all right, so let me just talk about some limitations of this work that we overcome in other works. One is that these techniques that I just talked about are inherently limited to giving CPA-style encryption. In follow-up work with Bartasek, Garg, Goyal, Malavolta, Reyes, and Roberts, we show that one can also get CCA-secure schemes, also maliciously secure variants of delegation, where the server can be fully malicious, you can outsource computation to it, and then ask it to information theoretically delete all your underlying data. We can also get obfuscation and functional encryption schemes with certified deletion. And there's also other results that do similar things, that do similar things for key revocation that I've cited here. The main insight in this work, in this other work, is to be able to achieve security in the presence of a partial decryption oracle. So it turns out that these BB84 state techniques are not really robust to giving out oracles that perform some sort of partial or full decryptions, whereas in CCA encryption and obfuscation, as you can imagine, you're trying to give some partial decryption oracles out. And so here, in order to do this, we use subspace coset states, which is a more entangled version of the BB84 state, and is robust to these types of decryption oracles. So that's all I will say about that. We also show in other work how to do publicly verifiable deletion, where the certificate of deletion can be verified publicly, and you don't need to hold on to X's and thetas and things like that in order to check deletion. Again, I won't say too much about it because I don't have much time. I'll just mention the results. We're able to build on the techniques that I just showed you to prove a Gaussian collapsing conjecture that first appeared in a work of Poremba. And from this, one can obtain public key encryption and fully homomorphic encryption with publicly checkable deletion from the learning with errors or the SIS assumptions. We can also show that injective trapdoor functions plus X for a variety of X's implies X with publicly verifiable deletion. Again, here I just want to say that it maybe sounds like this extra assumption of injected trapdoor functions is not ideal. So in other follow-up work, this can actually be improved to one-way functions or even one-way state generators, which, as heard probably, is potentially even weaker than one-way functions. It's a quantum variation on one-way functions, and that plus X gives X with publicly verifiable deletion. And then I would just want to mention that similar results were obtained concurrently and independently by Kitagawa, Nishimaki, and Yamakawa, who also showed that these assumptions are in some sense minimal. So this is the best you can do for getting deletion for all of these primitives. Yep, I think I'm already over time. So thanks so much for being here again. Happy to take questions.
Maybe time for one more question.
What are you assuming in particular for your obfuscation result?
For the obfuscation result, distinguishability obfuscation and one-way functions. Yes. Thanks.
Okay, so we'll take a break. Dakshita, thank you so much.
Thank you.
Okay, we'll be back at 11.